Hi, y'all. Welcome to the last big, in case you missed it or loved it so much you want to see it again. This is our last content heavy day, so the last real recording that is super substantial. So let's get right into it. Energy. Yay. So for this week, our goals are really energy, going over some core concepts, and also developing and applying self-directed learning. So we've got an activity today that's a lot less scaffolded. That may be a bit challenging to do on your own, but you can still definitely at least think about it. And then next session is a lot of feedback and reflection and sort of trying to tie together the whole experience of pose and think about how it's going to affect you moving forward. So a lot of self-directed learning practice. Going back over our intro to energy that we used last session. So energy is the capacity for doing work, and it can neither be created nor destroyed, but transformed from one kind to another. And all forms of energy are either kinetic, defined by movement, or potential, defined by position. So we have gravitational potential energy here and kinetic energy, sort of the macro level of motion with the velocity. And so these equations we've seen before, but just as review. So there are different types of energy, which are broken into two large groups. Potential energy, which is energy defined by position, and kinetic energy, which is energy defined by movement. And so sometimes people will use these to describe only sort of gravitational or that macro level kinetic energy of when you have a velocity, but there actually are other kinds. And so sort of we would spend a little bit of time brainstorming in session and thinking about the micro level of energy. And so, when you're thinking about kinetic energy, you can think of the particles. And when you're thinking of potential energy, it's not just gravitational. There's also, chemical energy and sort of all this stored energy between bonds and stuff like that. So thinking on the micro scale makes it really interesting and makes these categories. On the macro scale, so sort of the bigger scale, kinetic energy, there's really only one kind. And potential, we really talk a lot about gravitational and also springs come up a lot. So without further ado, there is this information online, and we'll also have the slides posted with sort of a rundown of a bunch of kinds in the notes. But yeah, feel free to brainstorm and try it out. So going into just the types of systems, an open system is a system in which both matter and energy is being exchanged with the surroundings. So think of like a hot soup in an open cup that's allowing both the heat and the water vapor to escape. This also relates to our bucket problem from session 8. So that was an open system. We have a closed system, so that is where only energy is being exchanged with the surroundings. So it's like a hot soup in a cup with a lid that allows heat to escape but no matter. And then we can think of an isolated system, so that is where no matter or energy is being exchanged with the surroundings. So like a hot soup in a perfectly insulated thermos, in our perfect world, that doesn't allow heat or matter to escape. So on that note, let's think about conservation of energy. The total energy of a system will be the sum of all the individual energies throughout the system. So it's going to hold true for any isolated system. Even when energy changes from one form to another, we know that it's not going outside of the system, so we know that that total energy is going to be the same throughout. And this is sort of related to our assumptions that we made in the ball throwing problem, how that kinetic energy was going to become potential energy and then become kinetic energy again. So let's start just chatting about gravitational potential energy. Gravitational potential energy is the energy that an object has because of its position in a gravitational field. The height of the object stores energy it can use to do work. So our equation is just the mass of the object, the gravitational acceleration, and the height of the object from the reference frame. So we can sort of see our origin here in our reference frame. So that's important in order to know the height. Then going into motion kinetic energy is the energy that an object has because it's moving. So the inertia of the object allows it to do work on other objects. Below is a formula for calculating kinetic energy on a rigid, non-rotating body. So thinking about it's a half times the mass of the object times the velocity of the object squared. And just to note that this is not a vector quantity, so it's more accurate to call it the magnitude of the velocity vector, and you can continue to represent it as v, but there's just not that vector notation. Then looking at elastic energy, so this is sort of what I was talking about with springs. When materials deform, they store elastic energy and can apply work as they return to their original shape. This equation below calculates the elastic energy stored in an idealized spring. So, just a little note, the signifier for potential energy is this U. So U sub S can be like spring energy, but the potential energy is generally represented by U. But anyways, we have 1/2 times the spring constant, and that is in units of Newton meters. And then the distance the spring is stretched / compressed compared to the spring's equilibrium length, and that distance is going to be squared. So on that note, we have this little think, pair, share problem that once again, I'm just going to read out and then pause it, try it on your own, and then I'll go over the solution. So we can use what we know about energy to simplify problems that would be more difficult to solve with free body diagrams and forces. For example, the spring below is currently being compressed 0.2 meters by the red box. As the spring decompresses, it will use all its stored energy to accelerate the 0.1 kilogram red box from rest. If the spring constant is 10 newtons, what is the maximum velocity of the box? Assume a frictionless surface. So pause the video, take a try. There's these equations in the top right. All right, so thinking about the solution. We know that the total energy is going to be that potential spring energy plus the kinetic energy. So initially, our potential energy is going to be 1/2 times the spring constant, which is 10 Newton meters, times the sort of distance from the original, so 0.2 meters squared. So that equals 0.2 joules for the potential energy. And we know that this box is starting at rest, so we know the starting kinetic energy is going to be 0. So the total energy is going to be 0.2 joules. Looking at the final energy, the spring is at its resting space, so it's going to be 0 joules. So we know that the total energy needs to stay at 0.2 joules, meaning the kinetic energy in the box has to now be 0.2. And so 0.2 joules equals 1/2 times the mass, 0.1 kilograms, times the velocity squared. We can solve that out, and we can get that the velocity has to be 2 meters per second in order to conserve that energy. Great, so we're going to enter sort of this big theoretical problem space, and I'm going to introduce it. If you feel comfortable and able, try it on your own, but we would be doing this in groups. So your first large project at Olin is the hopper project. You'll build a small bio-inspired hopping mechanism with lots of freedom around your design. However, it must still abide by some key constraints. So the ones that are important today, it must hop substantially according to its size, and its potential energy will be at most 3 joules. So imagine you're halfway through your first semester at Olin, and it's time to test the hopper you've made. You've decided to build a trigger mechanism that all the potential energy in your hopper is going to be stored in springs. So what we're going to ask you to do in session would be in teams is use the knowledge you already have and produce a plan for approaching the problem. We're not expecting you to solve all these answers. We don't even think you have everything you need to do it. And so it's really supposed to stay in that theoretical space of project planning and thinking about the concepts and equations you need, getting used to sort of approaching problems that way and breaking them down. So, on that note, what concepts and equations will you need to 1. Determine how much energy is stored in the hopper, 2. Predict the motion of the hopper, and 3. Find a reasonable way to measure the actual motion and compare results to your predictions. Just a little hint, reminder, you can always use visuals to aid your thinking. For me, that's always super helpful. No worries if that's not the way your brain works, but for sure a way to approach it. So if you feel comfortable, go ahead and pause the video, try this on your own. All right. So then just diving a little bit after this activity into what self-directed learning even is. So we've kind of talked about it a bit, but never specifically. And so in its broadest meaning, SDL, self-directed learning, describes a process in which individuals take the initiative in diagnosing their learning needs, formulating learning goals, identifying resources for learning, choosing and implementing appropriate learning strategies, and evaluating learning outcomes. So you can maybe sort of start to identify where we've tried to put things in to practice some self-directed learning into these sessions. And also sort of thinking about the spaces that we haven't touched upon as much and you'll probably get more experience with during your time at Olin. So, in session, your pro team would share out just some quick stories about their experience with self-directed learning. So I can sort of talk as someone who just finished the capstone project, and it's a very big project with a lot of open-endedness, and basically we're just given a prompt from a company and then given, what they want. We need to figure out how to get there. And so it's sort of self-directed learning at the peak. And so I had a really positive experience with my team and sort of they were really great. We were really autonomous and we were really able to sort of work in ways that made sense for us. And so like trying to be asynchronous and using certain resources. And it was not to say it wasn't challenging at times as well. Sometimes that open-endedness can be overwhelming. And especially since I was on the Ford design team, there were times where we felt as though we needed to make decisions that we weren't sure were the right ones. So it can be challenging because sometimes you feel like you're not the expert, but you still have to make the decision. But even with that, it turned out well and everyone was happy and we felt really rewarded to have been doing this work so independently and have been leading it so much. So just sort of thinking about self-directed learning is a wonderful thing, but it can be very challenging. And so just to acknowledge that, and if you tried this activity, acknowledge if this was hard, that's normal. And it will, you will get more skills to navigate it. And also you'll learn that those challenges are really a blessing. So we would end with some reflection today. So just, a few minutes per prompt, starting with how did you feel during this activity, and then moving into what connections did you make to previous educational experience and or moving forward about Olin. So take a few minutes to reflect on each of these. And that's it for session 9. So that ends our last content heavy day, and we really hope to see you for the wrap-up session. It's going to be a lot of fun and very casual. And so that's going to be a great way to tie off the summer and get you excited about coming to Olin. So awesome. Thanks for watching and hope to see you next session.